Welcome back to another video. Today we have Donsker's theorem, which is a form of a central limit theorem, but this time we do not have convergence of random variables to normally distributed random variables, but we have convergence to a Brownian motion, which is a collection of normally distributed random variables. One also says that this is a so-called functional central limit theorem because the limit is a function, so it's a path. And what is going to converge? Well, it's also sums of random variables, as in the central limit theorem. In particular, we're going to show that a random walk, in some sense, converges weakly to Brownian motion. There is some topology involved here, and general result about weak convergence, and that will take some time in this video. So, Donsker's theorem. Let me first try to explain the problem. So, what do we know about random walks in Brownian motion? So, we have ID random variables with variance sigma square and expectation 0. And if I sum them and divide by the square root of their variance, we know that this thing here converges to a normal distribution. And the normal distribution, let's call the limit here xt, so that's a normal distribution with 0 and t. And quite similar, you can do this for finite time points, and you only consider not the sum of all, but only the increments, like this here. And this then, of course, converges to the related increments of a Brownian motion, because they are independent, as the left-hand sides are independent, and they have the right variances. So you might think, well, didn't we just prove that the random walk, when viewed this here as a function of t, converges to Brownian motion? Because we've shown that x and tilde converges to x with respect to finite dimensional distributions. And we all know that finite dimensional distributions determine the law of Brownian motion uniquely. So does that mean that the stochastic processes converge? And the answer is no. And the reason is that we only introduced the weak convergence here if the two sides here have a joint state space which is to be Polish. And that's not the case here, because the functions from R to R, that's not a Polish space. So there's a problem still, and they have to be on the same space, and because they have to be on the same space, we just consider the continuous version of the left-hand sides of the random variables here. So how does this work? Let's take 1, 2, 3, 1, 2, 3. And the usual random walk looks like this. I have something here, and something here. But nothing stops me from just using straight lines here. Maybe this here, this, or let me even use color here. So nothing stops me from using this, this, and this. And the difference is not huge in absolute values, but the difference is that the green curve now has a continuous path. That's exactly what I did here in this formula here. So I used a linear approximation to approximate my thing here. Yes, like this. And now I can ask, well, the xn's are continuous, the x is continuous, is there a weak convergence? At least now the question makes sense. And we already know that finite dimensional distributions converge. But in order for all this to make sense, we would have to make the space of continuous functions a polished space. So can we do this? And the answer is yes, we can do this. And for this, we need a metric on the space of continuous functions. And the metric induces a topology, and that's the topology of uniform convergence on compacta. And, well, I just tell you what the metric is. So f and g are two continuous functions. And the question is, what's their distance? F and g, well, so this and this, f and g. You take their distance, their maximum distance up to time t. Well, maximum of 1, okay, let's take a maximum of 1. And you discount all this by e to the minus t, meaning that if the distance is further for larger t, it doesn't count as much. But this R here induces the uniform topology for convergence on compacta and makes C a polished space. So that's now we have everything. And now the V convergence makes sense, and the state space of the two things on the left and right hand side are in a polished space. But how do we show convergence? Well, what we would have to do is we would have to take continuous functions of bounded continuous functions of these continuous functions. And we would have to prove that the expectations of these bounded continuous functions converge. And that's pretty hard. There must be simpler ways. But let me first introduce two kinds of convergence I'm always talking about. I have here stochastic processes, and not only one of them, x, x1, x2, and so on, stochastic processes. And if they're finite, so if every time I take t1 to tk for any k, and the convergence of the joint distributions here occurs, then we write FDD convergence. FDD stands for finite dimensional distributions. On the other hand, if xn has paths in C and x also has paths in C, and if this here holds, as with our usual convergence in distribution, then we say that the stochastic processes really converge, and not only their finite dimensional distributions. And as I just said, that must be simpler as using continuous bounded continuous functions of continuous functions. Here is a result. The following are equivalent: convergence of stochastic processes and convergence of finite dimensional distributions plus tightness. Please remember what tightness was. Well, tightness, in the space of continuous functions, I would need to understand how compact subsets of the set of continuous functions looks like. And we'll do that in a minute. The proof of this here, we almost had that in our chapter on the convergence. So from 1 to 2, it's easy. First of all, we had that tightness follows from weak convergence just in general. On the other hand, evaluating continuous functions at specific time points, so like this here, this is continuous on the space of continuous functions with the convergence of uniform convergence on compacta. So these here, well, when these here converge, some bounded continuous functions converge, which are a subset of functions which I would have to check for this thing here. Which means from 1 to 2, that's okay. And from 2 to 1, okay, On the one hand, we have tightness, which means that tightness is the same as relative compactness, which means we have potential limit points from Prohorov's theorem. And for these potential limit points, we would need to show that they are unique. And we already know that we have finite dimensional distribution convergence. So the algebra of functions, which maps f to this thing here. So some bounded continuous function of the evaluation functions at time points t1 to tk. That's bounded and continuous. And this algebra, that's an algebra, and it separates points, which means that if you take two functions, f and g, you can find functions like this here, which are different for these two functions. And an algebra which separates points, we have shown somewhere in the V convergence result, that's a separating algebra, which means it can distinguish distributions. And we also had a general result, 927, that now V convergence follows. So, well, we have shown that 1 and 2 are the same. And now we, in fact, simplified what we had to do. So we only have to show finite dimensional distribution convergence. Okay, we have that for random walk to Brownian motion. But we have not yet tightness criterion for the random walks. And that's where the so-called Arcela-Ascoli result comes in. Maybe you've heard about this because I'm not going to show this, because that's from analysis, essentially. That's the Arcela-Ascoli result. And what does it say? A subset of continuous functions is relatively compact if and only if, well, something goes to 0 and at fixed time points something is nice. But the most important thing is this lim sup w goes to 0. So what's the w here? And that's called the modulus of continuity. So h here is a maximal time difference. Tau here is a maximal time I can plug in here. And f here is a function. And R is the metric on my state space, E. So WF tau H is the maximum increment between any time points S and T, which are at most H apart, which are both before time T. Okay, and this here has to converge to 0 uniformly. So the worst thing you can do with the F here, and, well, if h goes to 0, and if I have a continuous function here, a single one, then we know on the interval 0 to tau I have a uniform continuity, which means that the largest increment I can have between any time points s and t converges to 0 if the time increment converges to 0. So and that has to happen also uniformly for all f in the set A. Okay, so please keep this modulus of continuity, which is the largest jump between two close time points, in mind. Our goal is to show tightness of something, and now we know how we can show relative compactness of a set of functions, and that has to be connected somehow. And here's an intermediate result. So xn goes to xs processes if and only if they go to x in finite dimensional distributions. And the modulus of continuity, which is of course now random because the xn's are random, converges to 0 in some nice way. And once we have shown this, we again have simplified our result, because we have exchanged tightness, as we had here, by computing some expectation over some still not very nice object, this modulus of continuity. So how can we show this? Yes, how can we show this? So we have to show that this thing here is the same as tightness. And let me start with going from right to left. So I have tightness, and I need to show that the modulus continuity behaves nicely. And let me pick some tau and some epsilon. And k, some subset of bounded continuous functions, not CB, but I need a CE here on my state space of 0 infinity. Compact with, well, as usual in tightness, I need lim sub n goes to infinity. The probability that the n stochastic process is not in my compact set is at most epsilon. Yeah, by Arcela Ascoli, I can choose an H. So here, as we see, relatively compact, if and only if this here converges to 0, as H goes to 0. So I can take a small h such that this here becomes less than epsilon. Small h such that sub f in k, w of f, tau, and h is at most epsilon. And then I can put everything together. Lim sub over n goes to infinity, expectation of the w, xn, tau and h, minimum 1. Well, that's at most, well, for this w, two things can happen. The xn here is in my compact set, or it's not. If it's not, I can bound this here by 1, but the probability that that happens is at most epsilon, because of this thing here. And if xn is in k, I have that this here is less than epsilon. Yeah, so sorry, so again, so if xn is in k, then the w here is at most epsilon, so I can bound this thing here by epsilon. And the only thing which can otherwise occur is that the probability of w, xn, tau, h is bigger than epsilon. The probability for this is at most epsilon. So I have the bound that all this is less than 2 epsilon. But epsilon was arbitrary, which means that this limit here has to be 0. And we have shown that if I have tightness, then this equation here holds. Let's do the other way around, so from left to right. And I already know that I have converters of final dimension distributions. And I know that W is increasing in my H. So the W was this modulus of continuity, where I plug in a function, a maximal time, and a maximal time increment. And if the time increment gets larger, the maximal increment also gets larger, which means W is increasing in H. And by this, I can rewrite this equation well, first, the lim sup becomes a sup. For all n, limit h goes to 0. And rather than the expectation, I get the probability that Wxn tau h is bigger than epsilon. And that must be 0 for all h bigger than 0 and tau bigger than 0. So that's the same as my star. And I can still rewrite this. Well, for this convergence to 0 here, I could also say, well, it's less than epsilon, and it still would be the same. And I can also say the following: for all epsilon bigger than 0, there is a sequence Hn going down to 0, such that the supreme over all n probability of xn k hk is bigger than 2 to the minus k is at most epsilon times 2 to the minus k. So that's the same, because that equation here holds for all epsilon, so I can choose the epsilon from here as 2 to the minus k. And here, instead of equals 0, I can also write is less than something arbitrary, and I write less than epsilon times 2 to the minus k. But now my Arcela-Ascoli result tells me that the following set B, which is just the intersection over all k of all sets F, such that the modulus of continuity tau k, which I choose as k, and hk is less than or equal than 2 to the minus k. Yeah, this here is relatively compact, because as the Arcela-Ascoli result tells me, this model of continuity has to go to 0 uniformly if hk goes to 0, right? So this here goes to 0, then this supreme must also go to 0. If I'm in this intersection here, I know I can choose hk small enough such that anything smaller than 2 to the minus k comes out here, and that holds for every k. Yes, so that's relatively compact on the one hand side. On the other hand, I have that the supremum over all n, the probability that the n-stochastic process is not in B. Well, how can it not be in B? It must be not in one of these here. but the probability to be in one of these here is very high. The probability to not be in one of these here is at most epsilon 2 to the minus k, and I can bound the supremum by a sum. Sum epsilon 2 to the minus k, and the sum is, well, I'm summing over all k here, so that's essentially less, so that's less than 2 epsilon, which means I've shown that the probability that all xn's are in this relatively compact or compact set B is at most 2 epsilon. And that's, I've shown that the xn's are tight. Okay, now we have all this, and we come to the proof of Donsker's result. So that will be here, but we need one more step, one main estimate. Yeah, I need this estimate, and the reason why I need this is also clear. I need to control the W, the modulus of continuity, in the proof of Donsker's theorem. And for this, I need to bound the maximal increment. And here's a statement about the maximal increment. And the maximal increment, the probability that it's more than 2r squared of n, is bounded by this, which is a nicer object. I mean, I still have a probability here, but only a probability at one time point Sn. Okay, how can I show this? I'm starting in the numerator here, and I have t, which is the first time this thing here occurs. Then this probability here, well, it's bounded from below. Well, I just introduce one more condition here. But if that maximum is bigger than 2r squared of n, which that means I have t is less than or equal than n, and yeah, so this maximum is bigger than 2r square root of n, and Sn is bigger than r squared of n, which means that their difference is at most r squared of n. Yeah, this, so t less than or equal than n. Okay, that only depends on everything before time t, and this here depends only on things after time t, and I have the strong Markov property of the random walk, so these two things are independent. So on the one side I have this maximum here, because the t is defined as it is defined. I'm bounding from from below, which means I'm bounding this thing here by the minimum of this. Well, and this minimum here, I can bound it from below by first saying the probability that it's less than or equal is the same as 1 minus the probability it's bigger. And 1 minus bigger, I can use Chebyshev's inequality, 1 minus, and I get the variance of Sk, which is sigma squared times k. I'm dividing by the square of r squared of n, so r squared n. Still I have the minimum here, and the minimum here occurs at the maximum of this k here. And then I have 1 minus sigma squared over r squared. And, well, I can write further this here. I can have my 1 minus sigma squared divided by r squared. And I'm multiplying this here on the other side, and I have exactly my main estimate from here. Okay, now we have to set everything together in the proof of Donsker's result. we take sigma squared equal 1 without loss of generality. We need to control still the modulus of continuity, which means we have to control the maximal increment here. I'm also dividing by h, as I will need that in a moment. But as we have seen, this largest jump, well, that's the same. Yeah, that's not the same, but it's bounded from above, from below. Yeah, that's it. At most, this maximum here, this maximum absolute value of sk, and this square root of n here comes from this square root of n here. So that sum has to be at least epsilon times the square root of n. And I can use the result from the last slide. So this 2r here is now the epsilon. Yeah, like this. And okay, what happened with the denominator? 1 minus, okay, sigma square is 0, and the r here is my epsilon. No. No, wait, I have an n here and a square root of n here. So I would have to write an h here and an h here. And h is going to 0. So I have here sigma, so 1 minus r to the power of 2. No, 1 minus r to the power minus 2. But the r here is epsilon divided by h. So h square divided by epsilon square, but epsilon is fixed and h goes to 0, which means the denominator here vanishes. And I'm stuck with what I have here. The epsilon value is bigger than r times square root of n. R is epsilon divided by square root of h, and then times n. So let me briefly correct this. N times h here. So I have bigger than, okay, that 2 here comes from the difference between this 2 and this 2 here. All what I need to do is so the r is epsilon divided by h. Epsilon divided by h. Epsilon divided by h. Epsilon divided by h is my r, and absolute value of Sn, well, that's SNH, and the square root of n here is a square root of yeah, that's an h times square root of nh, and then without this thing here, I see that it's exactly correct that I have a square root of h in the denominator, and I could have used this like so. Okay, now nothing really happens anymore because we can bound this thing here. The SNH divided by square root of NH converges to a normal distribution, which means I can use the integral here, starting from this here. And because of this absolute value, that 1 here turns into a 2 here. But h is going to 0, and here we have basically something like e to the minus something square. And that's much stronger than the 2 divided by h here in front of it, which means that this thing here converges to 0. So we have shown this, and we are almost there. We just have to translate this here, the maximal increment, to an estimate on our w, like this thing here. We have to bound this. This here has to converge to 0, then we are done. Okay, we can certainly now choose for any delta bigger than 0 and small h that such that this here holds. So an h is here, from here. We've shown that it's converged to 0. That means we choose h small enough such that this here thing here is less than h times delta. So, and then with this we can bound the modulus of continuity, and all we need is the maximal increment between any times s, so kh and kh plus s, where k can be anywhere between 0 and tau divided by h, but the sup can be replaced by the sum here. Now we have the s between 0 and h, but for this thing here we know that that's bounded by delta times h. I have at most tau divided by h summons, which means that it converges here to tau times delta. But delta can be arbitrarily small, which means we have shown that this here converges down to 0. And that's what we wanted to have, and we have finished our proof of Donsker's theorem. And now let me end by yet another tightness criterion for continuous processes. And this here is based on the so-called Kolmogorov-Chentsov result that we already had, where we prove that Brownian motion has continuous paths. And here's a result for tightness that comes without the modulus of continuity. So I need to show that the increment, not the maximal increment, but the increment, and the alphath moment of the increment, in the worst case, where n goes to infinity, is bounded from above by t minus s to the 1 plus beta. Then the xn's are tight in the space of continuous functions. Okay, how can we see this? Just very briefly. So the proof is relatively similar to the proof of the Kolmogorov-Chentsov criterion for aversion or modification with continuous paths. I have Cnk, which is the maximal increment for times in the dyadic numbers which are 2 minus k apart. Then by continuity of all processes, I can bound W, well, that's the largest increment at 2 time points which are at most 2 minus m apart. And by this at most, I'm summing the psi n k's here, and that's bound from above. And you can prove that when this thing here holds, that this expectation here is bounded from above by using gamma is less than beta divided by alpha, bounded by this here. So alpha times beta is smaller than gamma, which means that this thing here converges. This thing converges, which means I can bound this thing here by some constant times t to the minus alpha gamma k. Okay, this here we had, I'm summing all these here from m to infinity, near to the power of alpha, which I also apply here. I'm using this inequality, I think. The alpha norm of this thing here, well, I can exchange expectation and sum at the expense of writing the norm, the alpha norm, inside of this. For this expectation here, I know it's bounded above by c prime 2 to the minus alpha gamma k. To the power of 1 minus alpha is this thing here. But gamma is positive, which means that this thing here has a sum. But now if m goes to infinity, since this here is a sum, as m goes to infinity, it's becoming 0. That means I've shown that the modulus of continuity goes to 0, and for this reason, I have shown tightness, as in the last result. Okay, great. So now we have shown a very important result. Donsker's theorem, convergence of random walks to Brownian motion. See you next time.